Go out there and see it. I enjoyed it. I thought it was pretty cool. But we're here to talk to you today about space communications. The group we work for is the Exploration and Space Communications Projects Division. There are 10 different projects within that projects division, including SLR, which you guys saw a demonstration of last night. You should have received a folder that has a couple of things inside of it. One thing inside of it is this educator's packet. Inside here, we have, I'm missing my front page. We have a number of activities that are in here that we'll be going through later today after our presentation. The other stuff that you see in there are goodies for you guys to take back to your classes. Bookmarks, lithographs, some fact sheets, some decals. Everything except for the decals, which are the stickers, are available for download via our website. So if you head to esc.gsfc.nasa.gov and then you scroll down, you will find all the publications right here. There are more publications, kind of hard to see them here. And then they're all available right there for download. So the lithograph that you have in your folder, the fact sheets, we've got some posters in here as well. They're a little large, so we didn't bring them by, but you're more than welcome to download those as well. But let's get started. All right, so you guys familiar with Prezi? Yeah. I hope nobody has motion sickness. Okay, so the first thing when it comes to space communications is this discussion of what exactly is communication. And communication is the activity of transferring information or the imparting and interchange of thoughts, opinions, or information or data. There are different types of communication. There's written communication, like what you have in your packets, verbal communication, what I'm doing right now, actions, gestures, symbolism, you know, like the yield sign that you see or the stop sign that you see while you're driving, or what I'm doing with my hands or sign language, and then visual communication, which is charts, graphs, pictures, etc. We use all these different types of channels for communication every day in our human contact, but we also use a lot of this communication, these types of communication when communicating in space. So the best thing to start with communication is the communication cycle and understanding how message is transferred from person A to person B or object A to object B. So we have Billy and Marge here. And Billy wants to tell his sister about the beautiful sunset he saw yesterday on his drive home from school. That would be the information source for the message. So Billy has thought of this idea in his head, but he hasn't quite transferred it over to his sister yet. So in this instance, he's going to be using a string can telephone, but it works just the same with simply speaking. So Billy is going to transmit his message. In this case, Billy grabs the string can telephone that connects him and his sister's room and begins to speak. As he is speaking, he is modulating the airwaves with his voice by vibrating them with his speech, which is also what I'm doing now, is to speak to you. Since Billy is sending his message into the string can telephone, the vibrations of his speech are carried down the string, transmitting his message to the other end of the medium, which is the receiver. Right now, I'm using airwaves to speak to you, whereas he's modulating his airwaves onto the string to send it to the receiver, AKA demodulator if you want to technical. Billy's sister Marge hears the vibrations that travel down the string and are amplified into the can next to her ear. Marge is now aware that she is receiving a message. And this is very important because at this point she knows that she's receiving a message, but she hasn't quite decoded decoded it, so it hasn't made it to the destination yet. Once Marge receives the message, she is able to understand her brother's description of the sunset. Now, in order for the message to go from the idea source / message to the transmitter all the way to the destination, there's a couple of things that have to happen. But first, this communication is also applied to communicating in space. So the idea source would be, we've landed on the moon. The sender, instead of Billy, would be astronauts, rockets, or different satellites in space. The carrier / medium that we use today are radio waves, for the most part. The receiver are our ground stations that we have all around the world. And the destination would be the NASA controllers on the ground and the data centers around the globe. We'll get more into this as we move forward. But as I was saying with the string can telephone, in order for the message to go from the sender to the receiver and finally the destination, we have to make sure that all different parts of the complications of communication are addressed. So there are certain factors that can affect how well your message is understood. So first of all, you have to be tuned in. So just like with radio signals in your car, if anybody has a radio, actual radio anymore, not a Sirius XM radio, your receiver has to be tuned into the right channel to understand the message. So if you're trying to dial into 88.5, but you're on 88.6 or you're on 88.4, that message is going to be very hard to hear because you're not tuned into the right signal. The other thing is reception. So in order to facilitate communication, the signal has to be strong enough to hear. If I was whispering, or if you guys were in the building across the street, you would be out of my reception area to hear what I'm saying. So for example, if you go out of your listening area, your radio station will change. I'm sure on your drive from Pennsylvania to Maryland, you probably went through a couple of different listening areas along your way, and your radio station might have changed or gotten fuzzy, and then you had to change it to a different one. That's because you were moving out of the reception area of that radio station. Interference and noise, this is a big one, especially for teachers, I'm sure. When a receiver is trying to understand the message from the sender, they may also pick up other interference. For example, noises from the playground make it difficult to hear your teacher yelling, "Recess is over." So either the message has to be loud enough or the noise has to be low enough for the message to make it through. One of the examples one of our engineers gave us is like with a dam for water. Either the river has to be high enough to go over the dam, or the dam has to be low enough for the river to make it over across. If the dam is, all the way, if it's taller than the water, then obviously the water would be stopped. Same thing works with communications. And lastly is language. In order for your message to be understood, you have to be speaking the same language. If I was speaking Russian to you today, you probably wouldn't be able to understand me as well as if I was speaking English. But the other thing is language can be any one of those 4 types of communication that we talked about. It can be verbal, written, nonverbal, or visual. So in the world of space communications, we speak in a language called binary code. And if our satellites or ground stations are not using binary code, then it's very hard for us to transmit the message from space down to Earth and to data controllers on the ground. So that was a quick overview of the communication cycle. Hopefully you guys all understood that and are able to understand where we are. Does anybody have any questions about that? No? Okay, good. So why does NASA communicate through space? There's a lot of different reasons for that. One, I'm not going to go into each one of these here, but this Prezi will be available to you through your, I want to call it Wikipedia, but that's not what it is. The Wikispace, yes. So you can go into each one of these extra sections if you'd like. But NASA communicates through space for a number of reasons. First and foremost, Satellites help us navigate, communicate, monitor the environment, forecast the weather here on Earth and throughout the universe. We have astronauts in space. We have astronauts on the International Space Station every day of the year. They like to talk to their families and they like to know what's going on and make sure that they're safe. So communicating with them is pretty important. I know that most of us like to know the weather report, and we like to know GPS, and we like to know that if we're lost out in the ocean on a boat that is sinking quickly, we can send a beacon to space, and hopefully the Coast Guard or someone can come out and find us based off of our GPS location. So those are just a couple of the reasons why we communicate through space. What medium does NASA use to communicate through space? Does anybody know? It was the string, and the string can't telephone. Waves. Heard that? Good job. So we use the electromagnetic spectrum, which is a way of showing the different types of radiation or energy that make up the electromagnetic spectrum, such as radio waves, microwaves, infrared waves, ultraviolet waves, X-rays, and gamma rays. For the most part, NASA uses radio waves right now. There are a few satellites out there that use microwaves. There are a few things out there that use infrared and visible light, like you saw with SLR yesterday. That's in the visible light portion of the spectrum, as you actually could see it. Everything else on here is invisible, but a lot larger than you might think. For example, radio waves are actually on average about the size, between the size of a football field and the size of a human being. So they're actually quite large. When you get down to the X-rays and the gamma rays, they're much, much, much smaller, like 10 to the negative 11, which is pretty cool. So electromagnetic radiation can be expressed in terms of energy, wavelength, or frequency. We use all three interchangeably here at NASA, so you'll hear that a lot. We'll talk about the frequency, we'll talk about the wavelength, we'll talk about the amount of energy being transmitted, and all of those terms relate in some way back to the electromagnetic spectrum. Frequency is measured in hertz, which counts the number of waves that pass by a point in 1 second. Another closely related property is wavelength, which is the distance from the peak of one wave to the peak of the next. So frequency is how many waves you see in a minute, whereas wavelength is the distance between those waves that you see in a minute. So from one peak to the second peak, that distance right there is wavelength. So the most common form of the electromagnetic spectrum that we are used to seeing on a daily basis is the visible portion of the electromagnetic spectrum. And this part of the electromagnetic spectrum consists of the colors that we see in the rainbow. You know, Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. And each of those different colors, I know this graphic is a little small, but each of these different colors relate to a different wavelength of light. So even though they're all part of one portion of the spectrum that we call the visible light portion of the spectrum, there's actually subsections in there for each one of the colors. So as I was talking before about language, satellites use the language of binary code to send messages from space down to Earth. Space communications embeds this binary code onto waves of energy, radio waves, infrared waves, visible light waves, to send and receive information from as far away as Pluto or Saturn to as close as the International Space Station. And even the internet connection that you guys have today uses binary code to send all of your messages from point A to point B. So binary code is a convenient way to represent almost anything using a series of ones and zeros. So this little paragraph looking thing right here actually says two words, hello world. You can imagine that all of the data that we send on a daily basis through the internet, through space, through GPS, is all being sent using ones and zeros. As I said before, radio waves are currently the most common carrier/medium that NASA uses. Radio waves are quite large, so they cover a large area when they're being sent down from space, which means that we have a better chance of capturing that message since it's sent over a broad space. And they have been quite reliable over the past 60 years or so, and they've turned out to be very useful for everyday communications as well as space communication. So who are the senders and receivers for NASA's messages? Anyone?
Deep Space Network?
There's one. Anybody else? Well, Deep Space Network is actually the only communications network that we will not be talking about today. So the Near-Earth Network, the Space Network, and the Deep Space Network are the three communication networks that NASA uses to communicate with our satellites in space. The Deep Space Network is managed out of the Jet Propulsion Lab in California. The Near-Earth Network and the Space Network are managed at Goddard Space Flight Center out of the Exploration and Space Communications Projects Division. So, I'm sorry, Deep Space Network fan, but we will not be talking about them today. But we will be talking about the Near-Earth Network and the Space Network, which are equally exciting. So, just a quick overview of the history of communications as far as space is concerned. When the United States was getting ready to send their first satellites in space, they needed to find a way to send messages back and forth to one another, satellites in space, controllers on the ground. So what NASA did is they constructed a network of these large antennas all around the world. Australia, Chile, United States, Canada, Norway, etc. They even put antennas on top of ships and planes to try to catch all of the data that possibly could be caught from every different place around the world. Because as your satellite is traveling around the Earth, you need to have a ground station and a location to capture that data. So over the past several decades, this network has evolved into what is known as the Near-Earth Network, which is managed, like I said, here at Goddard Space Flight Center, and the Deep Space Network, which is managed at NASA's JPL laboratory. Actually, that's Jet Propulsion Laboratory. You guys saw one of these huge antennas last night when you were out at the SLR facility, the one that kept moving around throughout the whole night. So those type of antennas that you're most common, or that you probably associate with communication, the large ones that you think of, those are the Deep Space Network. The Near-Earth Network uses a little bit smaller antennas, like the one that you saw last night, which was, I think, 13 meters across. Most Near-Earth Network antennas are between 11 and 15 meters. So the Deep Space Network antennas, those ones are the ones that are like 70 meters across, and are much larger. But the Near-Earth Network antennas are used to communicate with satellites in low Earth orbit. So like the polar orbiting satellites, the ones that are gathering all the information about the climate, the atmosphere, like GPM, the Global Precipitation Measurement Mission, or the Terra, Aqua, Aura of the Earth Observing System. Those satellites use the Near-Earth Network to dump their data as they pass overhead. So the Near-Earth Network has antennas all around the world, which I have here. And the Near-Earth Network is a little unique in what it does. So we actually have Near-Earth Network antennas that are owned and operated by NASA. Those are the ones that are in blue, like in White Sands, New Mexico, Ponce de Leon, and the Alaska Satellite Facility, and even a couple down in McMurdo Station, Antarctica. But then we also work with partner organizations and commercial organizations. so that we can have antennas literally around the globe. So we work with folks like the Alaska Satellite Facility, NOAA, the German Space Agency, the Swedish Space Corporation. So it really is an international effort to have that constant global communications that we now in this day and age expect from our weather reports, our climate data, et cetera, et cetera. So near-Earth network antennas can transmit commands to faraway spacecraft. In this sense, far away means in low Earth orbit. They can track the position and the speed of the spacecraft, which was what was being done by the SLR network that we saw last night. They can receive the science data from the spacecraft, and they can also do what we call TT&C, tracking, telemetry, and command data, which is, in the simplest terms, health monitoring of a satellite. So it lets us know that the satellite's on the right orbit, it's on the right track, it's healthy, its batteries are charged, its data is being gathered, et cetera, et cetera. So the near-Earth network antennas are pretty useful when it comes to space communications, and they're quite important to all of our satellites in space. Now, one of the issues with the near-Earth network antennas is their ability to communicate with satellites in space. So ground station locations are only able to communicate with the satellites in space for about 10 to 14 minutes as they pass overhead from horizon to horizon. So once it goes from horizon to horizon, our antennas can no longer see that satellite and therefore can no longer send or receive messages and or data from that satellite. Therefore, NASA put antennas all around the globe to kind of help, once one satellite makes it to one horizon, hopefully there's another antenna there to pick it back up and continue that process all around the world, which is why they had boats and planes and Antarctica and Chile and Europe, all of these antennas all over the place. Now, when the first ground networks were built, all these antennas were put in these very strategic locations for space communications. Unfortunately, political, environmental, and economical situations made it that we couldn't always rely on our antennas that were in, say, Baghdad, or Antarctica, or Norway, at the very, very tip of the Arctic Circle. Communicating with these antennas and relying on these antennas over the years got more and more difficult. So what NASA did from the early 1960s up until even today, they're still working on this today, they would evolve and merge their ground stations. So they would have one set of ground networks that were just around the equator, and then they'd have another set of ground networks that were just in the polar location. And eventually those would merge and they would evolve, and they would merge with the Department of Defense ground stations, and then they would merge with international ground stations. And eventually NASA came to the idea that we're gonna have to come up with a better solution. So in the 1980s, there was a proposal for creating a space-based communication relay system. And this was called the Space Network. So after astronauts have been to space and back to Earth, remember this is in the 1980s, so astronauts have already been going up to space in Apollo and Gemini. They've gone to the moon. The International Space Station is starting to be built. The shuttle program's coming online. So more and more astronauts are going to be going up into space over the foreseeable future. So beginning in 1973, the concept of a network of space-based antennas providing the communication links between spacecraft, astronauts, and ground stations on Earth was developed. This space network would consist of a constellation of communication satellites that would act as remote data sensors and essentially routing data around the clock 24/7 and creating 100% global communication coverage. So when the astronauts first started going into space, I'm sure you've heard that song, Rocket Man, and he talks about how, hopefully he'll be able to communicate with the Earth again by the time it comes around the other side of the moon. That was a big issue because you could only communicate when you were over on top of an antenna. And so if your antenna was down, or there was a storm, or there was a war, you may not be able to communicate with the ground until you came back over the antenna in the United States. So what NASA did was they built these antennas in space, essentially, that would act as routers. Just like your cell phone towers work with your cell phones now. That's kind of the concept for the space network. So part of the space network is the ground segment. We still need to have our antennas on the ground. And our antennas are located in White Sands, New Mexico, and Guam. So what we did was, starting in 1983, we launched the first tracking and data relay satellite. Oh, my pictures. And what tracking and data relay satellites would do is they were located in geosynchronous orbit, and they would be positioned over a single ground station 24 hours a day, 7 days a week. So in essence, by putting our TDRS satellites in 3 strategic places around the globe, no matter where your satellite was traveling around the Earth, you could always ping one of those TDRS satellites and get its data to the ground. And since that TDRS satellite was always above the ground station, since it was in geosynchronous orbit, which means that it was traveling at the same speed that the Earth rotates, you could always communicate with the ground. This was quite revolutionary, as it allowed the astronauts to do things like have an hour-long phone conversation with their parents, or do a Google Plus Hangout from space. It also revolutionized the way that we get weather data, GPS data, et cetera, et cetera. So, that being said, the Tracking and Data Relay Satellite Project is well in formation. As of right now, there are 8 Tracking and Data Relay Satellites, or TDRS, in geosynchronous locations around the Earth. In fact, TDRS-K was just launched in January of this year, and TDRS-L, which will be TDRS-12, will be launched in January of next year. TDRS is responsible for receiving signals from a variety of different missions, including the Hubble Space Telescope, the International Space Station, the Earth Observing Satellites, Aqua, Aura, Terra, etc. So you can kind of think of TDRS as the telephone company in space. All of those satellites that we rely on a daily basis to get our information, none of them would be able to communicate to the ground without the space network and without the TDRS satellites. There's a little bit more about TDRS in this section if you guys are interested in looking more into it. There's also a lot of items within that folder that talk more about the TDRS group of satellites. And we will probably be contacting you later this year when it gets closer to the TDRS launch. You can watch the TDRS launch on NASA TV. There'll probably be a NASA social. You can get all your kids around, watch the launch, which is pretty cool. All right, so now we know how the radio wave portion of space communications happens. But that portion of the electromagnetic spectrum is getting a little full. Most of our communications today, cell phone, GPS, space communications happens with radio waves. And so NASA is starting to look towards the future of space communication and looking past the radio wave portion of the spectrum. And one of the things that they've looked at is optical communications, or the infrared portion of the electromagnetic spectrum, which we are calling laser communications. So, what is optical communications? Now, optical communications is a term to describe the use of light to transmit data. So if we think back to Billy and Marge and their string can telephone, they were using their airwave, or their speech, to modulate the airwaves. and their transmitter in that case, or their medium in that case, were the airwaves. In optical communication, your medium is light. So that can mean using a flashlight to spell out SOS in Morse code. It could be flashing your headlights at someone as you drive by to let them know that their headlights aren't on. It can be the internet using fiber optic cables, sending infrared waves through the actual fiber optic cables. It can be as simple as using neon lights to say that you're selling coffee at that store. So that is what optical communications is. And I must note that what we saw yesterday with the SLR, although they were using the visible light spectrum and they were using optical communications in a sense, it is very different than what we're talking about here. With satellite laser ranging, there is actually no data being transmitted. It was simply a measurement tool. So that was not optical communications. That was actually just laser ranging, which is the difference. So what is infrared light? Infrared waves are a form of light having longer wavelengths than that of visible light. So it's very different than the colors that you see, the rainbow, the sun, etc. Infrared light is actually invisible to the naked human eye. And infrared waves are also much narrower than radio waves. Objects warmer than their surroundings radiate heat through infrared energy. So if you see the picture of the human on the right or the moon on the left, using an infrared camera, you can tell the differences of the heat being radiated from an object or an individual. But again, it's naked to the human eye. You must use an infrared camera for that. The remote control for your television also uses infrared light. When you point your remote control at your television and you push the volume up button, what you don't see is a little infrared laser being sent to your TV and sending that data to your television, telling it that you want it to turn the volume up. Now, if someone stands in front of you while you're trying to do that, and your TV volume won't go up and your channels won't change, that's because the laser from your remote control is not connecting to your TV. Therefore, the sender is not making it to the destination because of a complication. Now, the one form of optical communications that we're going to talk about is laser communications. Oh, real quick. Do you guys notice the difference between the picture on the left and the picture on the right? So the picture on the left is an example of what we get today with radio waves. The picture on the right is an example of what we could get in the future with laser communication. So why laser communication? When we were talking about infrared waves, I mentioned that they were narrower beams than radio waves. And when I was talking about radio waves, I was saying that they're actually about the size of between a football field and a human. So when we send radio waves down from space, they actually go over an entire size of the United States by the time they get down to Earth. And that's why we have those huge antennas all around the world, because we're trying to gather as much of that radio wave data as we can. So we'll keep sending our message over and over and over again, and hopefully, after 6 or 7 times, we've gathered enough radio waves to put that message together. And that's how you get your pictures of Hubble. That's how you get your climate data and your weather data and your precipitation measurements are all done through a series of send, gather a little bit, send, gather a little bit more, send again, gather a little bit more, and then put the pieces together and change the color and come up with a pretty picture and hopefully make something out of this data. So it takes a long time, but it's also very reliable because we know that the more that we send it, the more of the information we're going to get. And radio waves are not affected by the atmosphere as much as some of the other portions of the electromagnetic spectrum. But the difference with laser beams is that lasers using infrared waves are a lot narrower. So when we send a laser from space down to Earth, the amount of the beam getting wider is actually very, very, very small. It goes to from sending about 10 centimeters. By the time it gets down to Earth, it's only spread to about 40 centimeters, versus sending a radio wave from space, which is about 10 centimeters, to the size of the United States. So that means that with these narrow beams, we can put more data on that beam than we could with the radio waves. And we can send more of those waves faster than we can with radio waves. And the link will be much more secure because it's not being spread across a bigger space. It's going from point A to point B. So if you look at this graph here, you can see we've got LRO, which you guys heard a little bit about yesterday, the Lunar Reconnaissance Orbiter that is currently around the moon. Right now, using radio frequency waves in the Ka band, it can send about 100 megabits per second. The LADEE spacecraft, which is the Lunar Atmosphere Dust Environment Explorer, which will be launching later this year, can send about 128 kilobits per second, which is quite a small amount. To put that into perspective, the LADEE spacecraft can send a full-length HD movie down to Earth in about 600 hours or so. The Lunar Laser Communications Demonstration, which is NASA's first demonstration of laser communications in space, and will be launching aboard the LADEE spacecraft later this year, will be the first demonstration of laser comm from space, and it's hoping to do about 622 megabits per second. So to put that in perspective again, that same movie that LADEE would take 600 hours to send to Earth, LLCD can do in 8 minutes. So if you think again about all the stuff you've learned over the past couple days about the Hubble science data and JWST and Aqua and Orion, all these great satellites gathering data, they're running about the same speed as LRO and LADEE, which is pretty slow. And it's very long. And again, you have the puzzle that you have to put together at the end. So what NASA's trying to do with LLCD being its first demonstration is greatly increase that speed, the security, and the amount of data that we can send back down to the Earth.
What is that plan? What is that plan to be in operation?
So LLCD is launching this year, September 6, 2012, from Wallops Island, Virginia, which is actually quite close here, which is cool. And it will be aboard the LADEE spacecraft. It's actually going to be a module on top of the LADEE spacecraft. This is NASA's first demonstration of laser communications. Now, I think last night when we were at the SLR facility, we were talking about LRO and how LRO sent the Mona Lisa picture using lasers down to Earth. I'm not sure, was everybody here last night? Did they go to the SLR facility? Okay, so that was one of NASA's first attempts at one-way laser communications. So what happened with that is they sent a laser beam with embedded data, which was binary code that made up the picture of the Mona Lisa. They sent from Earth up to a receiver on the LRO spacecraft. What they then did was transmit it to radio waves and send the Mona Lisa back down to Earth using radio waves. So it was a one-way laser communication. That was our first, really our first try at this optical communications, but it only went one direction. LLCD will be NASA's first two-way high-rate communication system. So the other difference between LRO and LLCD is that they sent the Mona Lisa, which is pretty small. It's about, I don't know, maybe 1 gigabyte if that. So we're going to be sending 622 megabits per second. So we'll be able to send a lot more data, and we'll be sending a laser beam from Earth up to LLCD, and from LLCD back down to Earth. So there won't be any radio waves used, just laser.
So these things, like you talk about going around the moon and around the Earth, these are pretty high speed. I haven't done the math, but how do you take into account, or do you need to take into account the Doppler effect? Do you just have a big giant range out there, we're going to get it? Or do you actually have a tunable receiver to account
Yes.
for the tunable receiver?
Yeah, so what we actually have is we have the optical module aboard Goddard spacecraft, which can adjust accordingly to where the ground stations are. And then we have 3 ground terminals on Earth, one in California, one in New Mexico that's actually attached to a trailer and can be moved around, and one in Tenerife, Spain. So you kind of cover that side of the globe. And the other thing is that those ground terminals are fully movable. So they can look 360 degrees. And what happens with the transmission is, so the ground terminal sends a beam up to the LADI spacecraft, or LLCD, just like you saw yesterday with SLR, and it's kind of like a spotlight beam. So it kind of scans the sky, and then once it connects with LLCD, LLCD then sends a transmission beam down, which essentially locks their communication. And as the communication happens, they continue locked to one another. So that eliminates some of the, again, I can't think of the word, but when the beam kind of spreads out as it gets closer to Earth, it eliminates some of those issues because then they're locked with one another. Now remember, this is a demonstration. We've never done this before. It won't be 24 hours. It won't be 365 days a week. It's actually going to be about 2 weeks is the full demonstration. These optical terminals are brand new, so we are learning with this. This is demo 1. But the acquisition, the laser acquisition, is an issue that we are going to have to learn about in this experiment. We're going to have to make sure that the connections that we make on the ground are not only stable and secure, but they're sustainable over long periods of time.
I was just curious because last night they said weather interferes with the laser ranging about 45% of the time.
Yes.
So
We're also
it's a
in
lot
Maryland.
faster, but half the time you can't use it.
Well, we're in Maryland,
Right.
where it rains. And
Right. I mean, they said that applied to their
And that's true.
worldwide network.
Now, our ground terminals are in White Sands, where it's sunny about 364 days a year.
Okay.
In Southern California, where it's also sunny many days of the year. In Spain, where it's also very sunny many days of the year. So the idea is that having 3 different ground stations, if it's raining in California, Spain might be available.
Okay.
And if it's raining in Spain, well, White Sands might be available. And remember that White Sands antenna is on a trailer, so we can move that around if necessary. Weather does affect infrared waves. Just like when you heat up a thing of water, usually you're using some sort of infrared waves or visible light to heat that water up. So again, that's something else that we're going to have to learn with this experiment. Another reason why NASA hasn't done this in the past is because weather is a factor that we're going to have to overcome. But hopefully by doing this in phases rather than deploying a whole new space network with lasers attached to them, we'll be able to learn from this experiment, see how it works. LLCD, the Lunar Laser Communication Demonstration that I've been talking about launching this year, is step 1. The Laser Communication Relay Demonstration, which will be launched in 2017, is step 2. And that LCRD will be more like a TDRS satellite. So it'll be in geosynchronous orbit above a ground station 24 hours a day, 7 days a week. And so we'll be able to learn, if that's going to be a more stable way of communicating with optical comm versus an orbiting satellite. But yes, these are all things that we're going to think about. So real quick, back to lasers. What are lasers? Does anybody know that laser is actually an acronym? I was going to say, you're all middle school and high school teachers. So laser is an acronym for light amplification by the stimulated emission of radiation. And lasers are a very special source of light as they're composed of only one pure color or wavelength, and you can't break laser light up into other colors. So essentially with the laser beam, what's happening is that all of your waves, all of your infrared waves or all of your visible light waves are all waving together or in sync. So that means that when you send a beam of light from point A to point B, there isn't the, it doesn't spread out like radio waves do, as those are not in sync. Now lasers are used to transmit information in many different ways. I already told you about the remote control, but your CD players, if anybody has a CD player anymore, or DVD players, I don't know if anybody has one of those anymore either. But those use lasers. I have both. So scanners in stores that are scanning the SKU codes and all that stuff, they use laser beams. And then the internet. You know, going from dial-up internet to fiber optic internet was amazing. I mean, I don't know if you remember the SKU.
Oh, yeah.
And then hopefully 10 minutes later, your web page would load after you make dinner. That's essentially what we're trying to do in space, is go from the analog dial-up internet from yesterday into the fiber optic internet that we have today. And I'm pretty much done here. So let me play this video for you, and then we will let you guys take a break, and then we'll come back and do some activities. Oh wait, I don't know if this is gonna work. So that's a trailer video that we put together for the laser communication relay demonstration, which is step 2.
I was just curious, like energy budget wise, doesn't it take a lot more energy to generate an optical laser signal than it would like a radio wave?
Actually, no, it takes
No?
less energy.
Takes less energy.
And that portion of the electromagnetic spectrum is not as confined as the other portions of the electromagnetic spectrum. So we have a little bit more leeway getting into that. Now, moving into the future, that may change, but we are kind of coming in at the beginning of it. So hopefully we'll be able to establish optical communications for space now, so that when people start moving over into that infrared portion of spectrum, we'll already have a little bit of it cut out for ourselves.
And you can send that from Jupiter, they think?
Not right now, we can't, but hopefully, yes.
But they'll be able to find a beam.
Yes, and actually, transmitting lasers through space is a lot easier than transmitting lasers from low Earth orbit to the ground, because there's no atmosphere in space. So that question about the weather, that's not an issue in space, because there isn't an atmosphere to have it break up. Now the distance, the obstacles in the way, like asteroids and stars and planets, that's something we'll have to deal with in the future. But again, that second step, the laser communication relay demonstration, will hopefully address some of those issues, just like the Space Network did for low Earth orbiting satellites. Now, with the Deep Space Network, they send radio waves from Jupiter back down to Earth. But what they run into is the same thing that we ran into with the Near Earth network, that you can only transmit when you're exactly lined up, and you can only transmit for a few minutes. So everything has to go right in that transmission. Now with laser communications, it'll be the same way until we get a set of relay satellites that can transmit that beam based on where the satellite's orbit is and where they are configured. But again, that's a little bit further down the road. LCRD won't be launched until 2017. So once we start you know, once we establish optical communication and laser communications, then we can start looking past near Earth network out towards some of that deep space network area. So does anybody else have any other questions?
What buildings are the near network and the space network located in?
Well, we're actually all located in one building. No, I'm kidding. We are here at Goddard. We're located in building 12. They do all the management stuff out of there. There is a building here on Center that's a little more secure that does all the actual communications between TDRS and the antennas and all that stuff. They schedule all the different types of communications. But then we have our space network ground stations in White Sands, New Mexico, and in Guam that manage the actual, you know, acquisition of the satellite and the transmission and making sure that it goes from our data center out to NOAA or the Weather Center, et cetera. And then the Near Earth network is also managed out of Building 12, but each of the ground stations that we have around the globe have their own group that is in charge of managing that individual station. So they all talk to one another, but then they also talk to their, like if it's the German Space Agency's antenna, NASA contracts to use that antenna, but it's actually owned and operated by the German Space Agency. So there's a little bit of international cooperation as well as, you know, interagency NASA cooperation that happens. But for the most part, all of the management for it is done out of Building 12. Yeah.
One last thing, when the Red Accelerator went online, the public was worried about black holes being created in the center of the Earth. When you're talking about shooting lasers at the Earth, are you getting any flack yet from people worried about, oh no, you're targeting us?
Of course. Everybody's
really?
always worried about that. Are you going to kill birds or planes? You know, oh, certainly. You know, that's part of educating the public, is letting them know that A, these lasers are invisible. B, they're not high-powered enough to actually cause any damage to individuals on Earth. I'm not sure about the creation of black holes. But
Oh, that was a different project. The peak public panics.
I'm hoping that they won't cause black holes. But then again, your TV remote, you know, when I point my TV remote at you, it does no damage to you other than me being upset that I can't change my channel. So there is a lot of concern about that, but like I said, the lasers, the wavelength that we're using to send this data is invisible and it is non-harming. Now, as far as the atmospheric conditions that affect that laser and the data transmission, that is definitely something that we're going to have to look into. You know, and the same thing with birds and planes. They can fly by. It won't affect them, but it'll affect us because our data transmission stream will obviously be interrupted. So, again, those are some things that we'll have to figure out with this experiment and demonstration, and hopefully moving forward we'll be able to make optical communications the future of how NASA communicates in space. Anybody else? No? All right, well, what I'm going to do then is, if you guys would like, you're more than welcome to take about a 10-15 minute break. You'll come back here and you'll get your handy dandy folder and you'll get your educator's packet, and we're going to do a couple activities with you guys before you head out for today. So we'll meet back here, let's say it's almost 10:30, so 10:45.